In this video, we're going to take a look at a few different calculations involving nuclear decay kinetics. The most important thing to recognize about nuclear decay is it is always first order. So whether we're looking at the regular rate law or the integrated rate law, everything is always first order. Now, what can make this a little bit confusing is that some of the terminology is different for nuclear decay. It means the same thing, but there are just different words that are used. So for example, the first order rate law that we're used to seeing looks like this. Rate equals Ka raised to the first power. For a nuclear decay problem, it takes on the form A equals Kn, where A, activity, is used in place of rate, and N, number of nuclei, is used in place of concentration. When you're using the rate law, not the integrated rate law, but the rate law, the amount must be in nuclei. So whatever information you're given, you need to convert that to number of atoms, which is the same thing as number of nuclei. If you're using the first order integrated rate law, notice that it takes on similar terminology where we have, or I should say similar variables, where we now have N and N naught instead of A and A naught. In this case, N just needs to be some indication, some measurement of the amount. So it can be nuclei as written, or you could use grams or moles without needing to convert to actual number of atoms. So I'm going to say this again. For the rate law, the amount needs to be provided, entered into the equation as nuclei only, atoms only. But in the integrated rate law, you can use whatever amount term you want, because whatever you might do to convert that to nuclei will end up canceling because of the ratio. And then because this is all first order kinetics, the T1/2 equation that you use has to follow first order kinetics. This is probably a good one to memorize because we see it pretty often. We see it for all of nuclear decay. We see it for carbon dating, and then it's also used in integrated rate laws that are based on concentration and not nuclear decay when they're first order. So the first problem that we'll work on involves half-life. And just like we've done in some of the other videos, it's really important to define the terms, write down your starting equation, and then rearrange the equation, if necessary, to isolate the variable of interest. So in this example, we are given T1/2 for this isotope, and we're asked to calculate the decay constant. We're going to start with our T1/2 equation. T1/2 equals ln2 over K. We're trying to solve for K, so we need to rearrange this equation. And when we cross multiply and divide, we end up with K equals ln2 over T1/2. Like most calculations, it is really important to make sure that when you're entering the values, you are also including the units, because you want to make sure that the units make sense for whatever quantity it is that you're calculating. So in this case, we can see by looking at the terms that there should be a time unit in the denominator. So we'll plug in the values. We have K equals ln2 over T1/2, which is 60 years. In terms of the sig figs, the ln2 is exact, so we will ignore it for the sig figs, and this value, the 60, has 3 sig figs, and so our final result will have 3 sig figs. So when we do the calculation, ln2 divided by 60, we end up with 0.0116 inverse years. In this example, we'll define our terms first, and then we'll figure out which equation we need to use and take it from there. We're given a half-life of 305 milliseconds. We want to calculate the activity for a sample that contains a certain number of nuclei. So you can see here by the information we're given that we won't be using the integrated rate law. We don't have all of the terms that we need for that, and we'll be using A equals Kn. Now, while we are not given K directly, it is common to use the half-life equation to solve for K and then plug K into the equation. So that's what we'll do. We just rearranged this equation in the last example. So K equals ln2 over T1/2. So we have ln2 divided by 305 milliseconds. Ordinarily, it is fine to leave the time units for K or T1/2 as whatever they were coming from the other variable. In this example, we are going to report our answer in decay per second, which is the unit of becquerel. And it's up to us when we want to do that conversion of time. We can either do that here for the rate constant, the decay constant, or we can do that later. I'll go ahead and just take care of it now since we're talking about it now. So we need to convert that time unit to seconds. So we just apply our conversion factor. So we have 1 millisecond is 1 times 10 to the negative 3 seconds. Taking a look at our sig figs, the ln2 is exact. We have 3 sig figs coming from our half-life, and the prefix conversion is also exact. So we'll report our decay constant with 3 sig figs. So we have ln2 divided by 305 times 1 times 10 to the negative 3. Rounding to 3 sig figs, we end up with 2.27 inverse seconds. So the milliseconds will cancel. We're not done yet. That's just getting our decay constant. But now we can drop that directly into A equals Kn. So A equals K, 2.27 inverse seconds. So we're going to put that seconds at the bottom, multiplied by our number of nuclei, 1.07 times 10 to the 18. In terms of sig figs, we have 3 and 3. And multiplying this, we have 2.27 times 1.07 10 to the 18 gives us 2.43 times 10 to the 18 decay per second, inverse seconds. Or we can report that as 2.43 times 10 to the 18 becquerel. We'll continue to apply our similar strategy by identifying our terms and then figuring out what we need to do with that. In this example, we're given the value of K, and the question asks how many years, so that's a time. Does it take for some amount, that will be an N0, to decay to some other amount, which will be N. This is an example where we will use the integrated rate law. So we'll just write that out and then rearrange as necessary. ln n equals minus kt plus ln n naught. We're solving for time, so we need to get that kt term by itself and then factor out the k. First step, subtract the ln n naught. So ln n minus ln n naught equals minus kt. and then divide both sides by negative k. It is up to you whether you leave the equation in this format and do the subtraction, or apply the rule of logs and take the ratio. So just as a reminder, ln x minus ln y equals ln of the quantity x over y. I'm going to go ahead and use the ratio form here. Again, it doesn't really matter. It's just what strikes my mood for this example. So rearranging this, we have ln of the quantity n over n naught divided by negative k, and that gives us our time. Plugging in the values, we have ln of 0.0100 grams divided by 0.100 grams. This is what I was talking about earlier when I said it doesn't matter what the amount units are because they will cancel. So those terms will cancel and we're just left with a number that we're taking the natural log of, and that is fine. We now have this quantity. We have to divide by k. I'm going to put k as its own conversion factor, and we have 0.065695 inverse years, so the years will flip to the top. And that's everything that we have to plug in. Keeping track of our sig figs, over here for the natural log, we have 3 sig figs in each term. Once we take the natural log of that ratio, that will become 3 decimal places. And then we have 5 sig figs coming from the rate constant. So figuring out the sig figs for the log term, we have 0.01 divided by 0.1, and then we're going to take the natural log of that. And just to make a note of what that is, we have negative 2.303, giving us 3 decimal places. And the only reason I'm just jotting it down here is so I can make a note that those 3 decimal places will be 4 sig figs. I need to know that because that is what is limiting. So now if I finish the calculation, I'm just going to keep the whole value in my calculator for this example. I have that number. Oh, I did it again. I often forget the negative sign with my k. I caught it before I entered it into the calculator. All right, so now we're going to divide by negative 0.065695. Reporting this to 4 sig figs gives us 35.05 years. Our last example, we can tell, is a carbon dating example because we have information about carbon-14, carbon-12 ratio. So the information we're given is that it is 20% at this moment compared to that of a living organism. And we want to know how old is this object. Whenever we're doing these carbon dating problems, we're solving for time. So time is the age of the object. In this example, we're given the half-life of carbon-14, and we need to calculate K. So we use the half-life equation to do that. One way to look at this value, you notice I didn't mark it, this 20% value. One way to look at this, or I should say one way to think about it, is we know that it's 20% compared to a living being, which would be 100%. And if we do this math, we end up with 0.2. This is the ratio that goes into that ln term, and you'll see that in a little bit, but I just wanted to address how we can deal with this because it seems like we don't have enough information, but actually we do. So the first thing we're going to do in this problem, or I should say the next thing we're going to do in this problem, is we're going to calculate k. K equals ln2 over t1/2 equals ln2 over 5.70 times 10 to the 3 years. And when we do that math, before we do the math, let's think about our sig figs. ln2 is exact. Half-life has 3 sig figs, and we will report our decay constant to 3 sig figs. So when we do this math, ln2 divided by 5.70 times 10 to the 3, we end up with 1.22 times 10 to the negative 4 inverse years. And now we can plug this into the linear form of the integrated rate law. So ln n equals minus kt plus ln n naught. This is another example where the terminology or the variables gets changed. A lot of times for carbon dating problems, the n is replaced with a ratio. So a lot of times we'll see it like this, ln r and ln r naught. Rearranging the equation, it's going to look like one we rearranged earlier. ln r minus ln r naught divided by negative k equals t. And this is an example where you do want to bring this into that ratio form especially because of the way the information was provided to us. So we'll end up with t equals ln r over r naught divided by negative k. It's this r over r naught that is the 0.20 because we've already accounted for that ratio. Now we could have plugged both of these values in if we wanted to, because this is the r and that's the r naught. I kind of got ahead of myself and showed that to you a little bit early, but this is the way also to think about it if you don't want to do that calculation early and you actually want to plug in the r and the r naught. But since we already did that, we'll just plug in that 0.20. And then our negative k, I'm going to try to remember the negative sign this time. 1.22 times 10 to the negative 4 years goes to the numerator. Sig figs, we have 2 sig figs that will become 2 decimal places for the log term, and 3 sig figs for the decay constant. So doing the math, the natural log of 0.2 gives us negative 1.609. So our 2 decimal places is 3 sig figs. We have 3 sig figs from the rate constant, so our final value will be 3 sig figs. Let's see, divided by negative 1.22 times 10 to the negative 4 will give us a value to 3 sig figs of 1.32 times 10 to the 4, and that's units of years. And that is the age of the object.